What's up everybody, welcome to another video. Hope you're ready to flex those brain muscles. My last video was an introduction to how to find the domain of a function, and in this video we're going to continue that discussion by looking at some harder examples like this one, which we'll get to at the end of this video. So if you feel like you need an introduction, I'll have that video pop up in the top right, but I'll still do a really brief review. And let's start with what is the domain of a function. It's the set of all inputs, which are often x values, that produce real number outputs. But when we're thinking about finding the domain of a function, we're often thinking about what inputs don't produce real number outputs. What are the potential issues we have when we plug in a number that lead to what we call domain restrictions? And in our last video, we saw two of these. One happens when we plug in a number and we end up with division by 0. So for example, with this function f, if I plug 2 in as an input or an x value, I get 3 over 0. And remember, a fraction is a division. That's 3 divided by 0, which is undefined. So 2 is an input that does not produce a real number output. Undefined is not a real number. So 2 is not in the domain of this function. And so x does not equal 2 is what we can call a domain restriction. X does not equal 2. For the second example, when we have square roots or any even root, we could potentially have negative numbers under them, which are not real numbers. They are imaginary numbers. For example, if I plug 2 into this function, I get 2 minus 3 is negative 1. The square root of negative 1 is not a real number. And so this restriction is that whatever's under a square root or any even root has to be greater than or equal to 0. So we can say, well, x minus 3, the thing under the root, has to be greater than or equal to 0. And we can isolate x to say, well, this restriction is that x has to be greater than or equal to positive 3. So we're just adding 3 to both sides. So let's just summarize these two things real quick into a strategy for finding the domain of a function. We look for variable expressions in a denominator, right? Because this is when we could potentially have division by 0. Then we identify the restrictions by setting the expressions not equal to 0 and isolating x. So here, before this, we had a step where we could have written this out. X minus 2 cannot equal 0. We add 2 to both sides, and that means x cannot equal 2. So that's our domain restriction. So when we have variable expressions in a denominator, that gives us one type of restriction where we're excluding x values that make the denominator 0. And when we have variable expressions under a square root, that gives us another type of restriction, right? We need to restrict the x values so that we don't end up with a negative under a square root. So we do this by setting the entire expression under the square root greater than or equal to 0 and isolating x. And that's exactly what we did here. Okay, so we're going to apply this strategy in this video to these 4 examples. If you want to practice on your own, I encourage you, pause the video, pull out a pencil and paper, try to find the domain of each of these functions. These are the 4 we're going to go through, and I'm going to write the domain in interval notation and in set builder notation. I prefer interval notation. I really want to push students to learn that and get good at it, and I'm going to actually show you a good strategy for writing the domain in interval notation. And I just prefer it because that's what you're going to most commonly see as you get to more advanced math classes. So let's jump into this first example here. I see a fraction, I see a variable expression in a denominator, and so I'm going to say, well, we want to figure out what x values make this denominator equal 0, and we want to exclude those from the domain. So x squared plus 3x minus 10 cannot equal 0. So this is our domain restriction. We're taking the entire denominator and setting it not equal to 0. So how do I solve this? This is a quadratic. I'm pretty sure it's factorable. So I'm going to write these two factors out like this, or just outline them. And since a equals 1, I know we have an x here and an x here. And now what am I looking for? Two numbers that multiply together to negative 10, but add together to 3. So let's see, 10 and 1 aren't going to work. 5 and 2, that should work. Let's write a 5 here and a 2 here. And since they need to multiply to negative 10, one has to be negative, one has to be positive, and they need to add together to positive 3. So the positive has to be in front of the 5. We have positive 5 and negative 2, and now we can double check. These multiply to negative 10. They do add to positive 3. We're good to go. And so now we can apply the zero product property. And we could say we have two solutions. One is negative 5. That makes this factor 0. So x cannot equal negative 5. And the other is positive 2. X cannot equal positive 2. So we have these two domain restrictions. So to write this in set builder notation is actually kind of easy, and that's why kids often prefer it over interval notation. we can just say here's the domain of this function f. The domain is x belongs to the set of real numbers, that's what this means, and I just wrote a C with a little line through it, such that, what are the restrictions? We just put those here. X cannot equal -5, and then we can just put a little comma, x cannot equal 2. So this is a way of saying, in set builder notation, all the real numbers except for -5 and 2. So we've written the domain in set builder notation. Now let's write it in interval notation. And here's what I like to teach when I teach kids how to write this in interval notation, because it's often hard when kids first learn about it, is first represent this set on a number line and use your number line representation to write the domain in interval notation. I'm going to show you exactly how that works here. How do we represent all the real numbers except for -5 and 2 on the number line? Well, we can identify -5 here and put a circle. We want to exclude that, so we're going to do an open circle. 2 is bigger than -5. We're going to write it to the right. Make sure we line that up correctly. 2 is here. We're going to exclude that, but we want to include every other real number. So we're going to shade between the two. We're going to include all the real numbers bigger than 2, which is to the right on the number line, and all the real numbers less than -5, which is to the left on the number line. And now here's what's cool. We can use this to write the domain in interval notation because this lines up perfectly with intervals. So we can think of this as being one piece. We have from -infinity, that's all the way to the left on the number line, and we go all the way up until -5 and we stop and we don't include -5. So these open circles correspond to parentheses like this, right? Union, that's how we connect two intervals, right? That's our way of saying or. X can belong to this set or it can belong to this set. And our next one is the numbers between -5 and 2. So I'm going to write -5 here again using a parenthesis because we have that open circle. And I'm going to write 2 and I'm going to close the parenthesis again because we're an open circle. And I don't think I have room, so I'm going to have to write it down here. Union, sorry about that. And now I start back up at 2 and I'm going all the way forever and ever toward infinity. So we have the union of 3 intervals here, and that's always how this works. We can think of this as being 1, 2, 3 sections on the number line, and that corresponds to 1, 2, 3 intervals. This is the domain in interval notation, and hopefully you like that. Hopefully that number line to interval notation makes it a little bit easier for you. All right, let's try another example here. Here we have a fourth root. A fourth root is what I see. Remember, a square root or any even root cannot have a negative under it. So what's our domain restriction? Well, whatever's under the fourth root, which in this case is 2 minus x, must be greater than or equal to 0. Okay? We don't care about this -3 out in front. That does not affect the domain. Neither does this -1 out in front here. That's why I included this example. Kids get tripped up. We only care about what's under the even root. We're taking that out, and that's giving us our domain restriction. Few different ways to approach this. You could subtract 2 from both sides and then divide by -1. You just have to keep in mind that when you divide by -1, you flip the inequality. You could also just add x to both sides, right? The only tricky thing about adding x to both sides, let me show that. If we add x to both sides like this, we get 2 is greater than or equal to x. The tricky thing about this is kids have a really hard time interpreting what this means, which makes sense. What does 2 greater than or equal to x mean? I always like to write the x first. How can we write the x here but keep the inequality the same? Well, we can flip the direction of the inequality, okay? So we're just flipping it, and now this is a little bit easier to understand. X is less than or equal to -2, okay? So what does that mean? Well, we can write our domain, and we could write it in set builder notation like this. X is a real number such that x is less than or equal to 2. And that's one way to write it. And we can also write it in interval notation. So same exact thing. I'm going to first go to a number line. How do I represent the set x is less than or equal to 2 on a number line? Well, I'm going to find 2. I'm just going to label it wherever. And since x can be equal to 2, I'm going to fill that in. Okay, so filled in circle means x could equal that number. Open circle means x cannot equal that number. Okay, so we're filling that in. X could equal 2, or it could be less than, which is to the left, right? Less than or equal to. And so this corresponds to one single interval from -infinity all the way up until 2, but we're including 2 in the set. So that filled in circle corresponds to a bracket in interval notation, where the open circle corresponds to a parentheses in interval notation. So we found the domain of this function, we've written it in set builder notation, and we've written it in interval notation. Let's move on to this next example here. This is where it starts to get a little bit tricky. I see a square root and I also see a denominator. So there's a few different ways to approach this. I'm going to show one, then afterwards I'll talk about how we could have maybe done it a little bit quicker. So one way is to say, well, I know the denominator can't equal 0, so I'm going to take this entire thing. Let me make sure I leave myself room here. I'm going to take this entire thing, which is x plus 3, under a square root, and I'm going to say that entire thing cannot equal 0, okay? Now I can square both sides to get rid of the square root, or I can just think about, well, how does the square root of something equal 0? That's if the something equals 0, okay? So two different ways to think about it. X plus 3 cannot equal 0, and this means that x cannot equal, if I subtract 3 from both sides, x cannot equal negative 3. Let's confirm. What do we get when we plug negative 3 in? Negative 3 over the square root of negative 3 plus 3, which is 0. Square root of 0 is 0. Negative 3 over 0, you're right. The function's undefined at negative 3. That is a domain restriction, okay? So that's one way we could start, is we could just identify that domain restriction, and then we can identify the second one by saying, well, there's also a square root, so what's under the square root, x plus 3, has to be greater than or equal to 0. And we could say, well, that means x is greater than or equal to negative 3. Awesome. That domain restriction is that simple. X is greater than or equal to negative 3. So we are combining these two. What does that mean? X is greater than or equal to negative 3, but x also cannot equal negative 3. How can we combine these into a single statement? This is where it's tricky. X is greater than or equal to negative 3. X does not equal negative 3. And that's just into this one single statement. X is strictly greater than negative 3. So we're eliminating that or equal to, because when x is equal to negative 3, it makes the denominator equal to 0. And so we could have thought about that by just noticing that since the square root is in the denominator, we can take whatever's under the square root, and instead of setting it greater than or equal to 0, we could just set it greater than 0 and solve that inequality. That's one way to think about this as well. And I hope you try to approach future problems like that. When a square root's in a denominator, it changes the restriction. Now, what's under the square root can't be greater than or equal to 0. It can only be greater than, because when it's equal to 0, it makes the value 0, and that's division by 0. Hopefully that's making some sense. So let's write out the domain now. Let's write the domain in set builder notation. This is pretty easy. X is a real number such that x is greater than negative 3. And now let's write this on a number line. So we're writing a number line here, greater than negative 3. So not greater than or equal to, just greater than. So I'm writing a circle, open circle, because we're not including negative 3, only everything greater than it. So what interval corresponds to this? Well, remember, open circle corresponds to a parenthesis, negative 3, everything greater forever and ever. That's all the way to infinity. Hopefully that example made sense. Let's jump to our last one here, my personal favorite. Again, we have two restrictions. I see a square root. This time it's in the numerator. So we have that x plus 1 must be greater than or equal to 0. And we have a variable expression in the denominator. So we also have x minus 2 cannot equal 0. So two domain restrictions. So let's go one at a time. If x plus 1 has to be greater than or equal to 0, we could subtract 1 from both sides, and we get x is greater than or equal to negative 1. So that's one domain restriction here. X is greater than or equal to negative 1. If x minus 2 cannot equal 0, then x cannot equal positive 2, right? We just added 2 to both sides. So we have these two restrictions that we need to include together. So let's write out the domain. This is the hardest part. We've done the easy work. All right, so how do we write it out in set builder notation? Again, kind of easy. X is a real number. And one way to write it is just say such that, and just list out the two restrictions with a comma in between them. X cannot equal 2, and x also needs to be greater than or equal to -1. Now your instructor may have a problem with this. This is a way to write it. There's a better way to write it, which I'll show in a second, but it's hard to see the better way unless we see it on a number line. So let's first do that. Draw a number line here, and I'm including these two restrictions on the number line. So x cannot equal 2, so I want to find 2 and put an open circle there. X cannot equal 2. And x also has to be greater than or equal to -1. So greater than or equal to, -1 is to the left, so I'm going to fill it in because it's greater than or equal to. That's -1. So everything bigger than -1, but we're skipping over 2. We do not want to include 2 in the domain, okay? So here's how we can write it using interval notation. We can say we are starting at -1 and including -1. We're going to 2. We're using a parenthesis because we want to skip over 2. So that's our first little interval here. And our second interval is everything past 2. 2 and everything bigger from 2 to infinity. Boom. Interval notation. We've just written the domain. And that brings us to a slightly better way maybe to write the domain in a set builder notation. So let me go ahead and show that. We could use inequalities here, and this might be what your instructor prefers, which is we could say x is a real number such that, and let's use inequalities. X is bigger than or equal to -1, but less than 2, or x is greater than 2. And so this makes it a little bit more clear about what x values we're looking at. We're looking at -1 to 2, including -1, and then we're skipping over 2. So less than 2 or greater than 2. Hopefully that makes sense. So those are the 4 examples I have for you in this video. Hopefully this video helped. Comment below with any questions that you have to support me. Like the video, subscribe, do all that stuff. But most importantly, keep flexing those brain muscles, and I'll see y'all later.